All right. Hi, everyone. I think we're going to go ahead and get started. Hello, welcome to the National Operations Center of Excellence webinar, Active Interchange Management. My name is Kyla Elzinga, and I'll help facilitate today's webinar. The National Operations Center of Excellence, or NOCO, offers a variety of resources to support the transportation systems management and operations community. You can go to NOCO's website at transportationops.org to browse through links for TISMA resources and news. Previous webinar recordings and case studies can be accessed from NOCO's resources pages. I wanted to share a few logistics for today's webinar before we get started. We are recording this webinar, and the recording will be available on NOCO's website. All attendees are encouraged to stay engaged by using the Q&A feature for questions and the chat feature for comments. We will have time for questions at the end of all presentations, so if you have any questions, we encourage you to enter them in the Q&A area as they come to mind at any time. Also, please feel free to enter your name and agency in the chat to say hello to your peers. Now I'll hand it off to Reno to provide an overview of the agenda and to get us started. Thanks, Reno.
Thank you, Kyla. So I'll do some quick introductions in a moment, but first, welcome to the webinar. So in this webinar, we'll be presenting information on a concept that originated from some work for the FHWA Office of Operations on active interchange management, or AIM. So we'll learn about what AIM is and why it's important. We'll review what strategies are included in AIM, review a few examples, and summarize benefits. And then from there, we'll dive into a methodology to screen or assess an interchange problem for potential application of AIM strategies. We have a hypothetical example to show the application of the screening criteria, and then we'll wrap up the main portion of the presentation with some challenges. And then after that, we'll hear a peer presentation from Florida DOT on their development of queue warning systems at critical freeway exit ramps. So I am Reno Giordano of WSP. I work in our ITS national business line. I focus on transportation systems management and operations research and planning. I'll be joined by my colleague Les Jacobson of LNJ Transportation Consulting. He'll be also presenting on the AIM concept, and then Eric Gordon, Assistant Traffic Operations Engineer at Florida's Turnpike Enterprise, will present on his agency's queue warning systems, along with the department's consultant, Kelly Kinney of Jacobs Engineering. So let's start with, what is active interchange management? So AIM is a concept or an approach to analyzing and identifying active operational solutions to safety and congestion problems tied to freeway interchanges. So fundamentally, AIM applies the suite of established active traffic management strategies, but in a targeted, systematic manner, focusing on specific freeway segments at the interchange, along the ramp, and immediately upstream and downstream of the interchange. So it doesn't really introduce new strategies, new TISMO strategies per se. It's really more of a lens to focus active traffic management strategies on issues originating at interchanges. But of course, it doesn't negate a need to analyze a full corridor, as is typical when looking at these issues or strategy application. But with AIM, we can more efficiently address a couple of things. Number one, root problems with localized operational solutions instead of projecting that solution to a full order level, which often occurs for active traffic management strategies and could be a deterrent for logistical reasons or requiring significant investment. The second is we're looking at targeting problems that may be typically overlooked, particularly beyond those due to recurring congestion that may occur less frequently, but could still justify an operational strategy to be applied. So we're talking there about seasonal conditions, special events, or local traffic generators that cause high demands within short periods of time, not necessarily coinciding with peak period demand, in fact. And just so you know that the photo there on the slide is in Los Angeles. It's illustrating dynamic junction control, which is one of the active traffic management strategies under the AIM umbrella. We'll talk a little bit more about that when we get into the examples. So why is active interchange management important? Or why did we focus on applying active traffic management strategies to interchanges? So historically, safety improvements and congestion reduction at interchanges relied heavily on traditional infrastructure improvements, such as adding lanes, widening or extending ramps, or modifying ramp terminal intersections. But many interchanges, especially those designed and constructed several decades ago, have geometric configurations that make upgrading infrastructure to current standards time consuming and certainly costly. But AIM offers an operationally focused alternative that's more dynamic, more flexible, and actually more cost effective. In addition, AIM offers an alternative to more extensive corridor-wide operational solutions by focusing on the primary bottlenecks in most freeway corridors, particularly metropolitan regions. Those are the interchanges themselves. So AIM is important because interchanges are a significant source of safety and congestion problems. These occur due to bottlenecks, queue formation, and vehicles diverging or merging, which result in concentrated lane changing over relatively short distances. And research has shown that free flow capacities at these merge and diverge areas are less than elsewhere along the freeway corridor. So solving interchange problems may improve overall corridor operations. And as we know from TISMO more broadly, operational solutions themselves tend to be faster and less costly to implement than comparable infrastructure improvements, which in this case, we're talking about things like interchange reconstruction. So as noted, the suite of AIM strategies consists generally of a set of 7 or so active traffic management strategies that can be applied singly or in combination. So right now, we'll quickly review each of those summarized here on the screen. The first, adaptive ramp metering. Ramp metering uses traffic signals placed on freeway entrance ramps to regulate how often vehicles can merge onto the freeway. This strategy controls the volume of entering traffic and disperses platoons of vehicles that complicate merging movements. And algorithms dynamically adjust the vehicle rate entry in real time based on congestion levels. And the method is effective for both regular and unexpected traffic congestion. Of course, adaptive RAM metering is typically more effective when applied at multiple interchanges along the corridor, but when applied in this manner as part of a corridor management strategy, it can complement a more localized AIM approach. Second one, adaptive traffic signal control. So this involves technologies that collect real-time traffic data to dynamically adjust traffic signal timings and optimize the flow of traffic in a coordinated signal system. As a AIM strategy, adaptive traffic signal control can be applied at ramp terminals to improve the flow of traffic at those specific locations, managing the potential for backup up the ramp and potentially onto the main line. And adaptive traffic signal control is more typically coordinated with multiple signals along the corridor to be most effective. Third, dynamic junction control. Dynamic junction control does focus specifically on interchanges, in fact, although it's not doesn't have widespread use, which may be um, something to consider, maybe overlooked, but dynamic junction control dynamically assigns lane use on main line and ramp lanes at interchange areas where demand fluctuates throughout the day, and often there's an imbalance between that demand between the main line and the ramp. So using lane use control signals, mainline lanes can be closed or converted into exits, or similarly, shoulders can be open to manage entering or exiting traffic. So you can see that in the graphic on the screen, where a two-lane entrance ramp is merging with the main line, and the right lane of the main line is closed to allow left lane ramp traffic to merge unrestricted. So the idea is that there's heavy volume on the ramp, um, merging onto the main line, but the main line's volume is relatively less, and it is possible to close the right lane without causing mainline congestion issues. And the merging movement is better facilitated and safer. And dynamic junction control can be enhanced when combined with other corridor management strategies, such as adaptive ramp metering, or something like variable speed limits, to get to in a moment. And we have dynamic lane use control, which involves dynamically closing or opening individual traffic lanes as needed, using overhead lane use control signals. Usually advance warning to drivers is typically given through changeable message signs to encourage safe merging into adjacent lanes. And this strategy is often also used alongside things like variable speed limits and complements other strategies like part-time shoulder use and dynamic junction control. So part-time shoulder use itself dynamically enables travel on the shoulder based on congestion levels during peak periods and in response to incidents or other conditions during non-peak periods. This strategy is often implemented in combination with variable speed limits and dynamic lane use control. For interchanges, part-time shoulder use can add lane capacity along ramps or main lines to help merging or exiting movements. Uh, Queue warning. Queue warning involves the real-time display of warning messages, usually on changeable message signs, to alert drivers of upcoming congestion and slowdowns. In our case, those would be originating at interchange, merge, or diverge areas. So this strategy helps reduce rear-end crashes and enhances safety, and again, can be implemented with others, such as variable speed limits and dynamic lane use control. And then variable speed limits adjusts speed limit displays in real time based on traffic, roadway, and weather conditions. These speeds can apply to entire roadway segments or individual lanes, and the process helps reduce speed variations between the slowest and fastest vehicles, enhancing safety. So overall, we refer to those 7 active traffic management strategies in the context of AIM and addressing interchange problems as AIM strategies. So we can summarize them all here in terms of their objectives in the context of addressing these interchange issues. So again, for adaptive ramp metering, that would be improving traffic flow to allow a better merge. With adaptive traffic signal control, that's improving traffic flow approaching an entrance ramp or moving through the exit ramp. Dynamic junction control, the objective there would be to optimize lane use to improve merge conditions or to optimize lane use to minimize queue spillback. Dynamic lane use control is to optimize lane use to allow traffic to merge more effectively or to allow mainline traffic to exit more effectively. With the application of part-time shoulder use, that's to add lane capacity on the entrance ramp or main line to help manage merges, to allow traffic to have longer merge distances, or to add additional lane capacity on the main line to help manage exiting movements. And with queue warning, it's to warn drivers of slow to stop traffic at merge areas or slow to stop traffic approaching exits with long queues. And last, with variable speed limits, it's to inform drivers to slow down as they approach congestion at merge or diverge areas. So now a few uh, examples of these in practice. Got a dynamic junction control example I mentioned already, the queue warning example from Florida that we'll certainly hear more about, and the combination of adaptive ramp metering and part-time shoulder use in Melbourne, Australia. So in LA, the application of dynamic junction control can be found along State Route 110 northbound as you approach a left exit to I-5 northbound. Um, so uh, before the application of dynamic junction control there was significant backup during peak periods from that single lane left exit ramp, um, which backed up onto 110 through a series of tunnels as well, you can see in the images on the screen. So Caltrans decided to open the right shoulder of the exit ramp during peak periods to increase exit capacity, um, and then permitted the second left lane on 110 approaching the exit to be used as an exit lane to the ramp shoulder. So that can be seen in the upper image there, where the I-5 North OK sign is displayed upstream on a changeable message sign, indicating that both left lanes can be used to exit to I-5. During the off-peak, with the ramp shoulder closed, the second left lane reverts to a through lane only for SR 110. As you can see in the lower image, it just says 110 north only. And the results from implementing dynamic junction control here were pretty significant. Average ramp delay declined from more than 20 minutes to less than 5, and crashes were reduced by 30% as well. Second example we have is the Florida queue warning. I won't spend a lot of time on this one since Eric Gordon will speak about it. Oh, that was in this example, Florida's Turnpike Enterprise is installing queue warning systems along the Turnpike system in several counties to alert motorists to slowing or stop traffic backing up from congested interchanges. Radar devices detect traffic slowdowns or queues near ramps and then automatically trigger messages on changeable message signs to warn the drivers of upcoming traffic conditions. And those messages can be tailored based on congested conditions. Last example from Melbourne, Australia. So this is part-time shoulder use in combination with adaptive ramp metering. So in Melbourne, certain entrance ramps have an added lane for metered priority vehicles. Those vehicles are heavy trucks and transit vehicles. And that use of the shoulder on the ramp provides a queue jump uh, while all traffic is in fact metered entering the roadway. So the priority queue jump lane is closed when speeds are higher or volumes are lower, and opened during metering when merge speeds are lower. So this approach, and should note, this approach is also used where no priority lane exists. The shoulder is used simply for additional queue storage during metering operations. So the photos there show this. This is the on-ramp from Sunshine Avenue to the M80 Metropolitan Ring Road. The top photo shows where the priority lane starts, and the overhead lane use control signals indicate if the priority lane is open or not. And then the bottom image shows where further downstream at the merge point, where the priority lane merges with the standard entrance ramp lanes, and ramp metering is applied. So earlier I noted that one reason for focusing on active interchange management was to address often overlooked problems from non-recurring congestion that may occur less frequently but still justify an operational strategy. So this table kind of summarizes all that in a set of operational condition states. It does include those typical recurring conditions um, due to regularly occurring high traffic volumes or insufficient RAM capacity, insufficient mainline capacity. But we also have these other non-recurring conditions to consider for the application of active interchange management, special events, work zones, and seasonal conditions or day of the week conditions that act as those local traffic generators for high demand. The table suggests what the interchange-related merge or diverge problem is that AIM can address. So with special events, we're talking about event volumes entering or exiting the freeway, causing queuing. Those can be pretty substantial relative to the mainline volumes, particularly during off-peak periods, or work zones when construction activity causes queuing because of lane closures, narrowed lanes, or geometric shifts. And it can certainly impact interchanges pretty substantially. And then the seasonal or day of the week problems you can think about in that case, Friday afternoons in the summer, heading out of town to recreational areas, or in the winter to ski mountains in colder regions, increasing volumes significantly, impacting interchanges on a less regular basis. So just to summarize the benefits of AIM, obviously we've been talking about improving safety, and we've seen evidence of reduced crashes, reduced crash severity, reduction in near crashes. Operationally, we can see a reduction in congestion, evidenced by decreased travel times or increased travel speeds, less delay, more consistent speeds, and improved reliability. And then we can also identify improved cost effectiveness compared to traditional infrastructure improvements, and that's shown through improved benefit cost ratios, and of course, with an operational solution, increased operational flexibility, that you've got the ability to adjust your strategy operationally relative to less flexibility from a fixed infrastructure solution. And some of those benefits quantified here, mentioned the dynamic junction control example in LA with the substantial delay reduction and crash reductions. While they're not necessarily associated with single interchanges, we've got a few examples from active traffic management strategies as well, part-time shoulder use along US 23 north of Ann Arbor in Michigan, called the flex route there, which also, by the way, includes dynamic lane use control and variable speed limits. That's shown a benefit cost ratio of 3, along with some notable safety benefits, crash reduction of 17% or even 50% during peak periods. Drivers report quite high satisfaction with the operation. And the flex route is, that one on US 23 is currently being expanded further north to I-96 and applied to at least one other corridor in the state. For variable speed limits, a good example, the I-80 corridor east-west across Wyoming has shown significant safety benefits, crash reduction of more than a third, and a strong benefit cost ratio of about 9. And Q warning in the Twin Cities region of Minneapolis along I-94 has shown safety benefits of 56% crash reduction and 69% reduction in near crashes. So now I'm going to turn it over to Les Jacobson. We'll talk about a methodology to screen problematic interchanges for potential AIM strategies, and then a hypothetical merge example to illustrate it. Les will wrap up with some comments on challenges for applying AIM, and then quickly summarize a couple of products from this project as well. So go ahead, Les.
Thanks, Reno. So we have a flow chart that I'll get into, but it's pretty long one, and we can't really see it very well on a single screen. So I'm going to start with kind of a table to give you an idea of what the flowchart does, and then I'll walk through the flowchart as well, because I think it's a little bit easier to follow with a flowchart. At least it is for me. So the first thing we do is look to see if the interchange is really suitable for any of the AIM strategies. And really we're saying if there's significant safety or congestion issues, then it's probably suitable to consider strategies. If you've got a problem there that you want to address that isn't like that, there may be other strategies that you want to consider. In any case, if the answer is yes to that, you go to the next step. We feel that one of the most important aspects and most effective aspects of addressing interchange problems is ramp metering. So the first thing to do is say, is the ramp metered? And if it isn't, it's a good thing to think about doing. In either case, though, we still want to go beyond just ramp metering and see what other things there are, other issues and other strategies that you may want to consider. Uh, so the next step is to look at whether there's large variations in the main line and ramp volumes, especially during different times of day. If there are, for example, if there's a very high entrance ramp that may occur, that may create problems primarily in a shoulder time period or off-peak time period when there's room on the main line to get additional traffic into, you may want to consider dynamic junction control as Reno explained earlier. And if it's not suitable, go directly to step 4, which is looking at part-time shoulder use. So if you can widen the ramp shoulder or the mainline shoulder in the interchange area, and you can have that length adequate to make it make sense to have part-time shoulder use, then looking at part-time shoulder use, we suggest is something to do. In either case, we go to step 5 because there may be other things, especially around queuing and high speed. So the first thing we suggest after that is to look at variation in speed. If there's large variations in speed, kind of along the roadway or across the roadway, so that there may be discontinuities in flow, then you may want to consider the speed limit. And in either case, if there's a lot of crashes that occur or kind of unexpected queuing, then you should consider queue warning as well. And then kind of finally is to look to see if any of them were going to be going to be potentially beneficial. And if so, then you should continue. And what we mean by continue is to proceed with a more in-depth analysis of the applicable strategies to know which ones you do. So this is kind of a screening to see which ones might be beneficial. And then once you have those screened down, then go ahead and do a more detailed analysis. So just to show this approach in a flowchart, we start to look at if the interchange experiences safety problems or crashes, and if there's recurring congestion. If we see yes in any of that, then we go to the next step, which is again to consider the adaptive ramp metering. So if it's already metered, then we go to step 3. If it's not, that's something that you may want to consider to add to your active interchange management strategies. Next, as we mentioned, we look for dynamic junction control. And we suggest there that if there are large variations in mainline and ramp volumes occurring, you can do, you may want to consider dynamic junction control. And what that would do is kind of virtually changing the right lane of the entrance with the merge lane from, or the right lane of the main line with the merge from the ramp, and allow that ramp, encourage people to move out of the right lane so that there's more room for traffic coming onto the ramp. The hypothetical example will demonstrate that a little bit better if you're not certain what that's all about. After that is to look at if part-time shoulder use is needed. This could be on the ramp, or it could be on the main line to provide a little bit more merge length and room to merge into. And so we want to again look at the shoulders, and if you can get a long enough segment to make part-time shoulder use effective. And essentially, we move into the variable speed limits, checking to see if that is, and that's really just as in any other place, to look at if there's large variations in speed, then you might get people who come across variations in speed unexpectedly, and so variable speed limits can slow them down before they get to that congested location. And Q warning could go hand in hand with variable speed limits, or could be used without variable speed limits to be able to warn people of those speed discontinuities before they get there. And again, then just to look through all of these, and if there are some that have been identified, then you really do want to go through and look at some other sorts of things before you get to the analysis. You want to see if you've got the goals to improve the network, if your strategies support those goals. Also, if the agencies that are going to be operating it are prepared to operate a real-time active management system. And if those are answers are yes, then you go ahead and do the more in-depth analysis. So moving on with the hypothetical example, here we've got an area, a merge area, and this is not meant to be to scale, so don't be concerned about how sharp this merge seems to be. But what happens is there's a high demand entrance ramp from an airport that merges with a multi-lane highway. The peak ramp demand does not coincide with the peak mainline demand, so you get this surge of traffic from the airport not at the same time that the recurring congestion on the main line occurs. The mainline peak demand results in mainline congestion, and overall, this merge point is the corridor's primary bottleneck. It's also a crash hotspot, and the downstream main line has pretty wide shoulders. So to look at the screening process, in step one, we see that there's some crashes and congestion, and it's a candidate for active interchange management strategies. It may be that ramp metering would be effective. It doesn't have ramp metering today, and there's no other metering in the corridor. So ramp metering may or may not be appropriate there. Usually you want to have several ramps in a row in order to have ramp metering be effective. There are large variations in traffic volumes, and there are times that the main line during the peak volumes, the main line can't give up a lane to allow that merge traffic to come in. So it leads us to looking at dynamic junction control with downstream part-time shoulder use for the mainline peak period. So the off-peak, we could do junction control, and then during the peak, we would use mainline part-time shoulder use. So that would look something like this. This is the peak option where the shoulder lane is in place. The shoulder lane would be in operation and have a changeable message sign that would show that it was open. This changeable message sign here, I want to point out, but it's blank, so that this traffic coming on from the ramp would have a hard time merging into the main line. And so it's much more effective to be able to give them a lane that might go as far as the next interchange for them to merge into the main line. So when the airport ramp has its peak, there's much less traffic in the main line. And so that's when dynamic junction control might be more effective. You don't lose the refuge area of the shoulder, and the sign, the CMS back here, would alert drivers that there's a heavy merge from the right ahead and encourage them then to merge out of that lane to give more room for merging traffic from the ramp. One of the things that you'd want to consider is that there's a lot of fluctuations in ramp demand seasonally, and that's caused by flight delays. But and so having some things that are very flexible in terms of operation would be important. And also because there could be this unexpected queuing, including variable speed limits and queue warning is probably worth considering. So some of the challenges with any of these active interchange management strategies, some are institutional and educational. Are you and your partner agencies ready for something like this? Is the public going to understand it? What kind of education needs to be provided for both agency staff, but also the driving public? Also, do you have the funding to be able to do whatever your strategies are? Do you have the staffing that's necessary? Do you have a history of traffic management? Do you have the facilities to manage this effectively? You also want to think about design and integrating this into your overall transportation management process and scheme. And finally, is infrastructure expansion going to be occurring in the future? Are there some other things in the corridor that are going to mean that might have to occur? And just take that into account in your overall strategies and plans. So this project overall, we've got a few things that are coming out. There's a primer that will explain all of this in a lot more depth. There'll also be a shorter informational brief. And then we're planning on anywhere from 3 to 6 locations to have workshops that would actually apply this process to particular interchanges for an agency. that'll be coming up. So with that, we'll hold questions to the end, and we can move on to Eric to talk about their key warning system with the Florida Turnpike enterprise.
Yeah, thank you, Les. Sorry, I had to find the unmute button. We really appreciate this opportunity, Kelly and I, to join the NOCO team. Thank you so much for the invitation. We're going to talk about the queue warning system, of course. And today I'll be co-presenting with Kelly Kenny. Kelly's our TMC program manager, leading our queue warning software effort and all the operations as it moves forward. So she's a key and vital person leading the charge on queue warning. What I wanted to do was start off with a brief overview of Florida's Turnpike, super brief. We consider ourselves to be a vital part of the infrastructure here in Florida. We span over 500 miles. We're toll roads. We interconnect major cities, economic hubs, tourist destinations all around the state. So Florida's Turnpike Enterprise is a part of FDOT, Florida Department of Transportation. We designed the system for safe, efficient, and reliable travel for millions of residents and visitors each year. And we'll go into some detail on our queue warning system. So once again, thank you for allowing us to join you on the webinar today. One of the things that we talked about as a team, we looked at the history of what we've done with queue warning so far, and it's a continuing effort. We tried to think back, what was the start of this journey we've been on with queue warning? It was, in my mind, it was definitely a southbound crash on 429. I'll use my pointer to point to 429, approaching Interstate 4, I-4. I-4 is, of course, a key corridor between Tampa, Orlando, and Daytona Beach. This particular crash happened in February 2020. I remember it vividly, 2 women, 2 children dead in the multi-car crash. What we were seeing is that I-4 at that time, this was before the Moving Florida Forward project, which is currently underway and taking care of a lot of congestion issues on I-4. But prior to that time, we as a Turnpike talked amongst ourselves, what can we do on southbound 429 approaching I-4 to help out with this? We were seeing frequent queuing conditions, especially on Friday afternoons. One of the things that we recognize and we know is it's very difficult for TMC operators. They're managing a lot of different tasks. It's very difficult for them to manage these dynamic traffic queues. The back of the queues continue to move, and that can be a real challenge. So therefore, we talked with our continuing services consultant at the time, VHB, who is still helping out with us along with Moffitt, Nickel, and other teams. And we're looking at a more automated way and a better and more accurate system for these types of conditions. I know there's a lot of information on these initial slides, so I'll go fairly quick through these. The main takeaway is, if you recall, the fatal crash happened in February 2020. In this case, what we did was we split up our system into a northern queue warning and a southern queue warning system. State Road 91 is another term for Florida's Turnpike, and that's main road between Orlando, north of Orlando, and the Miami, South Florida area. Along with these, we included 528, 429. They're both in Central Florida. And then 589 is actually in the Tampa area. So during this initial screening, we worked with our consultant and said, where are we having the most challenges? What are the high priority locations on our system? And in this case, for the northern system, the Central Florida and the West Coast, we identified approximately 7 locations, including southbound 429 to I-4, the example from the fatal crash. Part of what we also included with this in the post-design services was the initial development of a queue warning software. One of the things I also wanted to point out, and we recognize that since this was a very new approach and new system for us, we wanted to include a very good and detailed concept of operation. So that was included as part of the initial queue warning systems starting in, again, May 2020. So here's a list on the southern queue warning systems. It also had some software components to it. And these are some other locations that are located in our southern region off of the Sawgrass Expressway, the main line, and then the extension that takes customers and travelers all the way to US 1 if you're headed to the Keys, let's say. After that point, we also looked at, once we did the initial northern and southern, we started looking at on a system-wide basis, what are some other locations where we could apply this at? And during that process, we actually added 12 new locations to that list based on our knowledge of where we were experiencing the most queues approaching these particular exits. So initially we started off by looking at what are the interchanges causing the most severe congestion for us, and what can we do about them in terms of queue warning? On this slide, I wanted to point out here that we talked with our team and felt the need to perform a very accurate analysis of where we were going to need to put, let's say if we needed a new dynamic message sign, where's the optimal or the best location for that dynamic message sign? Because every interchange experienced different level of traffic queuing. So what we did in this level of effort is we looked at it, we conducted an analysis report, we analyzed 12 different locations, and we worked with our team to try and approximate where the maximum queue might be. And then that enabled us to work with them to place the DMS, if it needed a new DMS, in the best and optimal location where we could. Going back to some of the locations we identified in the southern and northern and southern queue warning systems initially, and then we added the 12 new locations, we determined that not every location needed new infrastructure. It might have needed a new detector to help us, or it might have needed a new camera so we could have better visibility of those locations. Well, what we determined is that only a portion of the locations identified through the initial screening process really required having a new DMS. In a lot of cases, we were able to use existing infrastructure to facilitate the queue warning that we felt was needed at some of these locations. And then this is a great map of the actual turnpike system. So we have roadways that surround Jacksonville. This is State Road 589, which is Tampa area north of Tampa. So we did have a location there as part of our queue warning. And I wanted to point out the turnpike main line here going down all the way to South Florida. For anybody who's visited Orlando, this is the central spot of the tourism industry where my mouse is pointed right now. So next, I wanted to transition it over to Kelly, and she's going to talk a little bit about the benefits and to go into a lot more detail about the queue warning system itself. Thank you.
Thanks, Eric. So as Eric mentioned, I'm going to start with the benefits. And we saw 4 main benefits when we first rolled this out. We immediately noticed, as we were able to message dynamically for the end of queue conditions, specific to certain interchanges, but also just routine congestion locations, we saw a substantial reduction in a specific type of crash, rear end crashes, which often were, as Eric shared the story of that crash near Disney in 2020, they often had very significant injury or fatality. Promotes confidence in our motorist information. So we talk about TMC operators, and you have 4 or 5 operators trying to manage 15 or 20 recurring congestion and off-ramp backup during AM peak and PM peak periods. And not only are they trying to manage this, they're trying to manage where the end of the queue is and updating that dynamically on the signs so that people have accurate information as they pass under them. So this ability to automate this is allowing us to have that accurate information in real time on the signs and promoting motorist confidence in the information that they're seeing. Of course, increasing efficiency in our TMC operations. If they're not having to chase the queue and consistently update the DMS signs specifically during peak periods, they can focus on real-time management of events and dispatching of our resources, our road rangers and our specialty towing programs, getting incidents cleared quicker. And then we were able to provide this as a benefit to all of the Florida Department of Transportation districts. So we were able to share the software after its development so that at least 2 or 3 other districts are actively using it and others are interested in using it going forward. So it can really be deployed anywhere because we have a statewide ATMS platform. It's called the SunGuide software. Every district uses it. And this this queue warning software was specifically developed to work directly with that SunGuide platform. So all of the FDOT districts can use this product. Okay, so this is a brief summary concept. So I'm going to just kind of walk through it, maybe each component of it. On the left, there is a DMS sign. And then primarily what this software is using are NVDS detectors, so side-mounted radar detectors that are measuring speed and occupancy. The detectors are returning that information to SunGuide. SunGuide is communicating to the queue warning system, and that information is then being set to certain thresholds within the queue warning system. So you have a speed below a certain threshold and occupancy above a certain threshold. If those two conditions are met, then a message, a predetermined trigger message is sent to the DMS sign. So there's really no interface directly with the TMC operator. Their responsibility is to, create a congestion or off-ramp backup event and send that information to third-party nav systems and to, the statewide 511 system. But they're not responsible for, at that point, activating or updating the DMS signs. The software is doing all that automatically. Okay, so what are the trigger conditions that we have set up for our particular roadway system? Like Eric mentioned, we have a pretty large system, over 500 miles of roadway, spanning multiple urban areas. So there's a lot of different conditions that we saw merited a trigger. The first one was, of course, exit delays. And in this case, Eric mentioned that some existing infrastructure could be used, some new infrastructure was needed. So specifically for exit delays, you had to have an NVDS placement that was, fairly close to the exit or GORE area, or in a location that would be able to be triggered where you would expect the queuing to occur onto the main line. So if you happen to get sort of a gap in your location, maybe there was 1 mile downstream or a mile upstream, it really couldn't serve the purpose well of being able to automate the messaging for the exit delayed trigger. But the way this trigger worked is it is looking at lane specific. So it can be set up that it only looks at, a left lane or a right lane, whatever the need is. For that threshold condition, while the other lanes are not meeting the threshold condition. So it's almost like 2 triggers in one. The exit lane has to meet the trigger for low speed, high occupancy, and then the other lanes are the inverse of that. So if the ramp is queued and the main line is free flow, then it triggers that specific message on the DMS telling people there's exit delays and for the through traffic to keep left. In this case, it's keep left because the exit is to the right, but there's also instances like our service plazas, our rest areas are in the center of the roadway. So if there's exit delays into those plaza areas, it would of course advise people to keep right. And this is a real world example of an exit delay condition. So the image on the left is a snapshot from our camera. And if you've ever been to Orlando, you've probably driven this exact area. This is International Drive and the Beach Line. So this is where the convention center is and SeaWorld. So this particular exit does experience primarily special event related exit delays. And you can see here, we do have multiple DMSs that would be triggered from this particular right lane being delayed. And then in our SunGuide software here on the right, you can see how it's broken down specifically by lane. So in the exit lane, you can see the speed is very low, occupancy is high, and so that's why that lane has turned red, and that's what actually triggers this exit delay template is the lane specific trigger. But let's say that the DMS happens to be in an area where it's within congestion. Let's say, your interchange has backed up all of the travel lanes and you have a DMS in close proximity. So the software is designed to then look at a trigger that's telling it to look downstream at the first available NVDS that doesn't actually encounter congestion and do a calculation to say from the DMS to where that congestion condition ends, what's the distance? And then the message that we have scripted for that is congestion next so many miles. And that mileage will, of course, automatically update every minute with dynamically as the queue changes. So this is an example. We have an incident downstream. It's telling people, this is actually part of a two-phase message because our incident message does merge with our queue warning system message. So it would tell people that there's, perhaps a right lane blocked and also that there's congestion for the next 1 mile. And then the third trigger, as you probably guessed, is if the DMS is not within the congestion and it's not specific to an exit ramp, it's looking at downstream congestion that's not actually underneath the DMS sign. It's some distance ahead of the sign or downstream of the sign. So if it's free flow at the DMS, it's going to look at every downstream detector within, we have it set up for a 10-mile radius, and determine if the conditions are met for the, like I said, the low speed, high occupancy, and then it will calculate what the distance is from that DMS to where that first detector that encounters the congestion is. And again, this will update every 1 minute. So if you're looking at a peak period congestion where it's growing, the operator doesn't have to worry about updating that end of queue condition. The sign will automatically update. So here's an example, and this is this is a location that's approaching US 1, which is the exit to the Florida Keys. So at the very, very south end of the turnpike, we installed in this queue warning project a new DMS sign at mile marker 4. And then when the ramp to the Florida Keys backs up, which this is sort of a holiday weekend or special event, you can see in this case, it's backed up about 2 miles from US 1 to our camera at the 2 almost. The DMS sign would automatically note that there's congestion 2 miles ahead. So I briefly mentioned that in the SunGuide software, if you have an ongoing incident, let's say there's a crash or emergency vehicles, the incident message automatically merges with the queue warning message. So you're letting people know that critical piece of information, like the lane blockage associated with an event, but then you're also merging that with that critical piece of information of when they can anticipate they're going to come to a stopped or slowed condition. And this is automated. It's a setting within the software, so the district who uses the software can choose to use it or not use it, or you can leave it up to manual intervention from the operator to merge when they feel appropriate. But we do automate this at the turnpike so that all incident messagings will be auto merged if there's an available queue warning message. And then part of the analysis that we do is we generate several dashboards. This is an example of one of them where we're looking at what type of messaging we're using and when it's most activated and on which signs it's mainly used by. So the graph on the top left is showing sort of an AM peak and PM peak when we see the queue warning messaging activated, and then what message the public is seeing. Like I said, we go up to 10 miles away for the way that the software is looking at triggers, and then the total duration per DMS. So a DMS on our southern section in Miami, it's very prevalent to see a queue warning message on there. Congestion starts around 5:30 in the morning there. And then started looking at some before and after analysis. I just pulled this one example because this kind of goes back to the very beginning story we saw about how this queue warning project kicked off. And it was from that very tragic accident we had on 429. So we installed, as part of the project, we installed a new DMS at mile marker 3 on the 429 southbound to try and mitigate the crashes that we saw from the I-4 exit delays. So before we had queue warning, for about the 18 months prior to that, we saw the crash or versus post queue warning, we saw a crash reduction of about 78%. And as Eric mentioned, there were also improvements over the last probably 6 to 9 months on I-4 as well to increase some capacity in that area. So the delays are not as substantial as they once were. But we found that even before the additional lane had opened on I-4, we saw a significant reduction in rear end crashes and a reduction in the severity of the crashes. And that was across the board at several locations that we evaluated in the Orlando metro area. And it was really location specific. There were some locations that we evaluated where we didn't see a reduction in crashes. other perhaps mitigating circumstances or some visual barriers, sightline barriers to where the end of queue is. So maybe some additional needs there, but it's been highly successful in several locations we've evaluated. I will mention that although we did start this project in just a handful of devices, and like Eric mentioned, we did a lot of evaluation on where it would be most needed and where we might need additional infrastructure. As time went on, we saw so much benefit that we really did decide that this could be used system-wide. So all of our DMS signs across the system, 130 signs, we set up the software to be able to auto-generate looking downstream for 10 miles, set up for exit delay conditions within the queue, the DMS within the queue conditions. So every single mainline sign on our system is now set up to auto-generate this queue warning message and auto-merge with incident messaging when appropriate. So some of our current efforts, one limitation we found is that right now we only have one data source feeding this system, this software, and that's our VDS data. And so we're looking at additional data sources to kind of fill in some gaps. If you have a widening project or a major infrastructure improvement where VDSs sometimes are temporarily removed, or you have an outage, where you have a gap in VDS coverage, you're left without a lot of good information to push to the queue warning system. So we have a current project right now to implement here probe data into the queue warning software so that it can be used in place of or in addition to the VDS data to kind of fill in those gaps. And then some future efforts is potentially using smart work zone devices. These are, construction projects, usually within our widening projects. They put out equipment on the side of the road as part of the construction to monitor just their specific construction zone, being able to integrate that data back into queue warning. And then we're starting a pilot with an AI camera detection. It's called Activision into our SunGuide software. And then if the speeds and occupancy can be detected via the camera, and especially the critical part of that is that it can be lane specific. So you can look at things like just an exit lane versus the through lanes and make the differentiation between exit delays versus congestion on the sign. But using that information to feed into queue warning as well, so that we have, up to 3 or 4 different sources of data that can be feeding the system and providing the best, most accurate information. I think that's it for us. Eric, did you have anything to add?
No, thank you, Kelly. Yeah, explaining that we've expanded it beyond those initial interchanges to be more applicable to system wide. And we did get one question in the chat, but I'll see if our facilitators would like to, how they'd like to handle questions. But thank you, Kelly.
Yeah.
All right, thank you everyone for presenting. Great presentations there. Really appreciate all the visuals and really good content. So we do have one question in the chat. And Kelly, I think this came a little bit early on in your presentation, but if you want to touch a little bit more on this. So will the queue warning be created automatically in the ATMS system or need manual input by operators?
So it can function 100% automated. There was originally in the discussion, we were developing the ConOps, there was, do we want to have an alert pop up to the operator for them to approve the messaging? But given the dynamic nature and the number of, congestion locations, we decided that we wanted it to be fully automated. And then we do a lot of, just quality control in real time. And then we added an element where anytime a queue warning message is activated on a sign, it then puts a timestamp into the what we call the event chronology, or the report that the operator is working on for the congestion in that area. So it's kind of like you set up a radius of how close you want an event to be to the sign, that it will timestamp automatically. So then as the operator is working their event and they're reading through their event chronology, they can see those DMS signs have been timestamped into their report as they were activated automatically by the queue warning system.
Great. And if you have questions, put them in the chat or in the Q&A box, everyone. We have another one come in. How dense do you need VDS sensors or other parameters to help you decide when you include a distance to the back of the queue in your messaging?
So we felt confident in 1 mile spacing that we could provide pretty good accurate information in near real time. But I will say that for the most part, the Turnpike does have half-mile spacing of their VDS detectors.
And Kelly, do you think that with the introduction of the probe data, that's going to be helpful, no matter what type of spacing perhaps you have? But yeah.
Absolutely, yeah. I think the one limitation we might see with the probe data is the ability to differentiate individual lanes. We'll see how that works as we work. We're hoping like in the next month or two, we'll be able to start implementing some testing with the probe data, but there might be some limitations with the lane specific monitoring.
I have a couple that came direct to me that I'll jump in on here. So are there any situations that your operators modify the queue warning messages? So like when would they kind of manually update them, if ever?
So we don't ask them to manually change the message. We do ask them if it's not accurate to blank the message and report that so that that particular VDS detector can be disabled. It's sort of one of those situations where bad data in is bad data out. So the only way that a queue warning is going to generate a bad piece of information or inaccurate piece of information is if a VDS detector is feeding it bad information. So we would immediately need to make a determination. Okay, was this VDS struck by lightning? Is this part of a construction zone project where a lane has been shifted and now it's reading the wrong lane? And do we need to disable and recalibrate or replace, troubleshoot that device?
Great. This one's for Kelly and Eric too. What kind of comments or public feedback have you gotten about the Florida queue warning system?
So Eric, I don't know if you want to take that one.
Yeah, that's a great question. What kind of feedback we've gotten? Well, there was a time when we were messaging a little differently on our system, but we've really been emphasizing the queue warning. And I think what we're hoping, and I'll ask Kelly to expand on this. I think what we're hoping is that the queue warning is something very actionable as they're driving along. So what we're doing our best to make sure is as accurate as it can be. So I haven't gotten a lot of direct feedback on that, but what I'm hoping is that when they drive along, they see that message, they take appropriate action. We're trying to provide something to them that's beneficial to them in real time. So we're actually continually looking at our DMS messaging policy and how we message. And I don't think we've heard any concerns, but going back to the previous question about the VDS sensors, we have encountered situations where we have had a sensor not function well. And so that's a case where we have to, and Kelly hit on it, our operators, it's super important that they take action whenever they see something that it doesn't seem like it's producing the right information. If you want to add on that, Kelly, go ahead.
Yeah, I think that the dashboarding also helps with that oversight just because we're looking at very specific site activations. So you really shouldn't be seeing a lot of 2 a.m. activations for a queue warning software unless there's an incident that's causing a queue. So it allows us to kind of go back to the day before or the week before and really evaluate, are we getting the right activations in the right places at the right time? Because the real-time review can be challenging as well. But I think public feedback, unfortunately, with a lot of what we do is traditionally, you're only going to get feedback when it's something negative. You don't get a lot of positive. So I will say that part of manual messaging and trying to chase the ends of queue is, the nature of that is that it can be inaccurate. And that's when you get the negative feedback. So I think, maybe no feedback is good feedback, but we haven't specifically looked, or asked for that feedback related to the automated system.
Yeah, great. Thank you. Another question in the Q&A, are you concerned with the latency of the HERE data?
Yeah, we did some testing before we asked for the development of the HERE data into QWS, where we were very satisfied with the latency. It was very close to real time. But I think that as we move forward into this project, there's going to be a 90-day testing window where we look at a direct comparison of our real-time VDS stats and the here data stats and try and make the determination of exactly what the disparity is and make sure that it's, providing the best, most accurate information we can get. So we don't have the answer to that yet, but hopefully soon.
Great. Great. I have a couple of questions, I think, back to Les and Reno's presentation too. So in the hypothetical example, why not just open the shoulder to traffic all the time?
I think I can take that.
Okay.
The reason is that even though there's enough width for a shoulder use lane, if you had that open all the time, then when there were crashes, you couldn't get vehicles off the roadway, and especially in lower volume, higher speed conditions, dark conditions, that could be really important. So if we can preserve that refuge for as long as possible, I think that's a safer solution.
Okay, great. And then I think more about some of the general AIM strategies. How could adaptive signal control be used as an AIM strategy?
So adaptive traffic signal control would pertain to a signal at the end of a ramp to essentially flush out backup that may be occurring from heavy exiting volumes. And I think even in the case, maybe I didn't mention it, but even in the case of an entrance ramp, similarly, it could be coordinated with or used in the same manner as something like adaptive ramp metering, where you're controlling the movement of traffic onto the entrance ramp because of a negative merging situation. And in the case where it might be paired with adaptive ramp metering, you only have so much queue space on an entrance ramp, and the signal could be used in a manner to control that too. Otherwise, you'd run into a situation where you'd be flushing the entrance ramp and overriding the ramp metering itself. So effectively, it's the terminal of an exit ramp or the beginning of an entrance ramp to control ramp traffic volumes and the merge and diverge movements onto the main line subsequently.
Great, thank you. Okay, I think I've just got one more here, so if anyone has other questions, get those in. Back to Kelly and Eric, for agencies who are starting to look at key warning systems or really exploring kind of technologies out there, what kind of advice would you give, or things, lessons learned or things that you wish you would have known as you started this process?
Great question. I'll start it, and Kelly will probably give a better answer than I can. It's been an iterative process. I think for us, like we started off initially in 2020 after the crash we had on 429. By May 2020, we were starting to identify specific interchanges where we felt like we had the biggest challenges. I think our messaging itself has changed over time. I want to say that we've modified it so that I think the messaging you saw that Kelly shared today is a little more applicable. What we're challenged with is the queues kept moving, right? So when the queues moved beyond the DMS, it's in a lot of cases, the messaging didn't seem to really be applicable. So I think, Kelly, we've adjusted the messaging quite a bit. I think maybe if you want to consider doing something like this, think about your existing infrastructure, think about what you're starting to work with, and identify the locations on the system where you feel like you have the most trouble. And in fact, I think we're going to probably borrow a little bit from the AIM processes after this. So this is my first exposure to AIM. And so maybe there's an iterative process you can follow to try and identify the hot spots and where to start. Start with existing infrastructure, then figure out where you can build from there. And I'll let Kelly jump in.
I think that's excellent advice. I think it'd be great to have a standard guidance or flow chart for something like to build out something like this. Using using agencies like ours experience. In the operations side of things, I guess my advice would be kind of determine what type of triggers you're looking at, because as time went on, we found additional needs. At first we didn't have a trigger for when a DMS was within a congestion. So we were not sort of satisfied with the message that it was producing when the congestion was under the sign. Or we weren't, we weren't 100% satisfied with the ability to historically look at what type of messaging was used for the delays on Friday on, the beach line at iDrive. Like we had a hard time, getting reporting and looking back historically. So that's when we started looking at, okay, well, let's timestamp these devices into our reports and let's make it so where the operators can see, see this information more readily so that they can do some quality control. So there's a lot of considerations, a lot of things we enhanced over time. I'd say we've probably been through, maybe 10 versions of the software as we've grown and built additional enhancements. But I think it'd be good to standardize something like this.
Great. Well, I don't think we have any more questions. Any kind of final comments from our presenters? Anything else you all want to add before we wrap up here?
Nothing from us. I'll certainly thank again our peer presenters from Florida. I think that really helped enhance kind of the real world application of some of these interchange considerations we were looking at. So thank you.
Great. All right. Well, I just want to thank everyone for attending today. Really appreciate your participation, and big thank you to all our speakers. So thank you all for being here. Great content. Just want to share again that a recording will be available on the NOCA website in the next week or so. And just, yeah, thanks everyone for joining us. Really appreciate it and hope you have a great rest of the day. Thanks, everyone.
Thank you.
Thank you.
Take care.